In my talk, I'm going to describe a little bit about the noisy measurement files, or like Michael said, the primitive mechanism answers, um, and more specifically, the geographic regions on which these queries were actually taken. So my goal here was to try to preempt as many questions as I could, and I thought most of the questions that I thought of were related to the geographic regions that we use within DAS. And before moving on here, I also want to give a shout out to the rest of the science team for help editing these slides. And the usual disclaimer, like Michael said, all views expressed here are my own. Okay. So I'll start by describing the original geographic spine that was used within DAS, and then I'll move on afterwards to, I'll use this afterwards as an example to describe geocodes and define those. And then after that, we're going to talk a little bit about the AIAN spine, which was a precursor to the optimized redistricting spine, and then I'll talk about the optimized redistricting spine itself. Then I'll conclude with some implications on all of this for the noisy measurement files, as well as papers and other resources that might be helpful when using the noisy measurement files. Okay, so top-down algorithm uses a discrete Gaussian mechanism to answer counting queries in a hierarchical set of geographic regions, or a geographic spine. So that's the definition of spine here. In this graphic on the left, we have a proper subset of this middle of these geo levels. In the middle are the standard census spine. So for example, I'm also defining geo level here on the second bullet point. So for example, the standard spine is defined by nation or US, and then state, county, and then on down, census tract, block group, and block. And then one other thing to note about the graphic here that I'll come back to later is that the AIANNH, or AIAN for short, areas are included here at the block level and kind of off to the side. I think the author probably, I would imagine, did this because it doesn't really fit into any particular geo level very well, which I'll return to later as well in the slides. Yeah, it's kind of it takes up some geo levels fairly large amounts of certain geo units, and yeah, it include in many geo levels, so especially at county and below. So in my final bullet point here, I'm defining geo unit and child geo unit kind of by example here. So New Jersey is one geo unit in the state geo level, and one child geo unit of New Jersey is Middlesex County. Yeah, so you can think of this as a directed acyclic graph for those of you that are familiar with that. Okay, and then, so this spine is encoded using geocodes. So for the standard census spine, using that as an example, the block level, so that's the lowest geo level, the block level geocodes are in the format given here. So each one of these different segments has a different interpretation. Yeah, so together with the geocode widths given in this format string, as well as the block geocodes themselves, you can derive the entire spine. So, and the reason how that's possible is the next point here. So the geocode of each geo unit contains the geocode of its parent geo unit. So there's a nice recursive pattern here. For example, if we have a block geocode, we can remove the last 4 digits to figure out the geocode of its parent block group geo unit. In other words, we can find what blocks need to be aggregated together in order to derive that block group parent geo unit. And just to keep this property working all the way up the spine, we also define the US geo units geocode just to be an empty string. So you can kind of think about this format of the geocodes as having on the far left side here, you can kind of think of an implied 0 width segment that corresponds to the US or nation geocode. And that recursive formula can be used all the way up the spine. Okay, and then I also have an example here of a geocode 34023. So if we suppose we were given this geocode, and then suppose we're trying to figure out which geo unit this corresponds to. So first of all, we can look up the state FIPS codes. Those are just available online. And going to the format string here, that would be a 2-digit code. And we can figure out just from looking at the state FIPS codes that the 34 corresponds to New Jersey. Okay, and then we can look at the New Jersey County FIPS codes and find that 023 corresponds to Middlesex County. So this geocode as a whole corresponds to Middlesex County, New Jersey. Okay, so now we'll talk about some of the original impetus for kind of looking at alternative geographic spines to the original one that we used within DAS. So we had two different reasons to look at alternative spines to improve accuracy in certain regions. The first one is by far the most important especially for redistricting. That is that, and I believe Michael touched on this as well, that geographic regions that are on the spine tend to be more accurate than those that are not. And we can also make a more general statement here by defining something that Michael already alluded to as well. So we're going to define the off-spine entity distance as the minimum number of on-spine entities that we need to use in order to derive an off-spine entity. And that's a mouthful. So I also have an example here. Suppose we're given Prince George's County, Maryland, -1 tract, so that geographic entity. And we want to find the off-spine entity distance. Well, we can derive that off-spine entity by taking Prince George's County and then subtracting a tract. So we use two on-spine geo units to derive that off-spine entity. So its off-spine entity distance is 2. So counts in geographic regions that are closer to the spine in terms of this off-spine entity distance are generally more accurate than those that are further. And this, like I said before, this is by far more important than the next one here, especially for redistricting. But we've also found that when the number of child geo units of a given parent geo unit, which we call in the DAS team the fan-out value of the parent geo unit, is large, the accuracy of counts in the child geo units tends to be lower. More importantly, on larger schemas than the redistricted file, this can actually cause computational infeasibility, just because we're trying to solve optimization problems at that point that are so large that we have a little bit of trouble with our actually being able to solve them in a tractable way. Okay, and then next we have a precursor to the optimized redistricting spine, and that is the AIAN spine. This uses the standard spine as a starting point, and the one and only change that it makes to the standard spine is that it adds 2 different branches. At the state level and below, there's an AIAN branch, and there is a non-AIAN branch. So as an example here, there are 2 geo units in the state geo level that are within the geographic region of Arizona. That is one that contains the AIAN portion of Arizona, and then one that contains the remaining portion of Arizona. And these branches continue all the way down to the block level. And and then I have here at the bottom which AIAN areas we actually used when creating the spine. So this wasn't a very large change from the standard census spine. So unsurprisingly, the implementation was fairly straightforward as well. It just involved adding 1 digit to the geocode that we talked about before. And that digit was at every geo unit from the state level and below, we added an initial digit that was either 0 or 1. 0 corresponded to a geo unit that is outside of the AIAN branch, and 1 corresponded to a geo unit that is inside of the AIAN branch. Okay, and that was the starting point for the optimized redistricting spines. And this is the actual spine that we used in the redistricting run for PL 94. Okay. And the goal here was I like to think of this as moving to the Pareto frontier. So we only make a change to the AIAN spine when it will not increase accuracy in any GeoUnit on the AAN spine, and hopefully, ideally, increase accuracy in at least one unit, GeoUnit. In other words, basically, we are not using anything like mean squared error or any average error over all the GeoUnits on the spine. It's much more like a Pareto optimality idea here. And we also, but we have more flexibility with block group because that's not really legally or politically defined geo level. So yeah, we have a little bit more flexibility there. So we also replace block group with the optimized block group. This definition of optimized block group is intended to increase accuracy in certain off-spine entities that I'll describe in a little bit here. So just from a very broad general level, the two steps for defining the spine is to first define optimized block groups. And then afterwards, we are going to perform a bypassing operation where we bypass child GeoUnits whose parent GeoUnit only has one child. Or in other words, we're bypassing child GeoUnits that are only children. Yeah, that's kind of a way you can think of it. Yeah, and I'll talk more about that in a second and talk about why we do that. Okay, so the four different sets of off-spine entities that we are intending to increase accuracy on with this spine are given here. So you'll notice that each one of these is a partition of the US. So when, in some cases, I will just add a final GeoUnit at the end that corresponds to the remainder of the US, just to ensure that every block in the US is actually exists inside of at least one element of each set of off-spine entities. So for the first example here, in the AIAN OSEs, these are composed of individual AIAN areas along with one additional off-spine entity defined by the rest of the US. Okay. Yeah. So, and then second here, we have each group quarters or GQ OSE is defined by the union of all blocks that contain the same combination of major GQ types. As an example of this, one group quarters OSE is the union of all blocks that only contain group quarters that are college and university student housing. And yeah. So next here we have the minor civil division or MCD OSEs. These are composed of MCDs in the 12 strong MCD states. So these are states where MCDs actually play an important, more important government role in the government. And we're going to add one additional element to this set of OSEs that's given by whatever's not in our initial definition here. And finally, the place OSEs are composed of incorporated and census designated places that are outside of these 12 strong MCD states. So outside of these 12 strong MCD states, incorporated places tend to play a more important role in the government. So we're going to optimize accuracy on those instead of minor civil divisions. And we're also going to add one final element to this set of OSEs given by the rest of the US. Okay, now we're ready to describe how optimized block groups were defined. So each optimized block group is defined by the intersection of a tract, an AIAN OSE, a GQ OSE, an MCD OSE, and a place OSE. Okay, and this grouping operation is designed to avoid both high fan-out values by only grouping a certain number of blocks within the block group, and also designed to keep these block groups geographically contiguous. And the final step of the spine optimization routine is to bypass the only child GeoUnits. And the reason this is done is because the parent consistency constraints within the top-down algorithm. These GeoUnits, after we already fixed the estimate for the parent, there's really no purpose of observing any primitive mechanism output for the child GeoUnits, because the parent consistency constraints already have them fixed anyway. So instead, we move the precision up to the parent so that we're actually using all of our available precision. Okay, and then there's a few implications on noisy measurements that I'll end here. The first one is kind of the most obvious, that we use geocodes to actually organize these. And also, the queries answered by the primitive mechanism vary by geo level. So if you see that total query has a primitive mechanism answer for the block group, a geo level, for example, that doesn't mean it actually will actually have an answer for a given block geo unit. Okay, and for any given geo level, the proportion, so we're talking in relative terms here, of each geo unit's total precision that is allocated to a given query group is the same for each geo unit in the geo level. So we do keep the relative allocations between the different query groups the same across the geo level. However, the total precision of each geo unit within a given geo level is generally not equal. And sometimes it can even be zero. Because, for example, if a geo unit was bypassed, we may allocate zero precision to that geo unit then, or we would allocate zero precision to the geo unit. Finally, here we have the format string for the optimized redistricting spine. It's 31 digits long. I'll just focus on the two ends of this format string here, because those are the ones that are easiest to interpret. So the GeoUnit is in the AAN branch of the spine if and only if the first digit of its geocode is 1. And the second and third digits, assuming that it's at the state level or below, the second and third digits correspond to the 2-digit state FIPS code. And the 6th to 8th digits provide the 3-digit county FIPS code, assuming that it does have at least 8 digits that will correspond to the county FIPS code. So for all block GeoUnits, the final 16 digits provide the standard Census Bureau 16-digit tabulation block geocode. And that's just done to probably more information than you need, but that was just done so that we could easily convert this the block GeoUnits to the standard census spine afterwards for things later on in the pipeline. Okay, and then I'll end here with some papers and other resources that I thought might be helpful. So like Michael said, we have a forthcoming paper in the HDSR that's coming out that just describes the top-down algorithm. Also, more information on the geographic spine can be found in this working paper, which I recently added to archive, so it should be available just by searching for it on Google Scholar as well, or by using this link in my slides. And also the code is available online for the production run redistricting code. And that's all I have. Included my email here in case any questions come up during while looking at the noisy measurement files. Thank you. Thanks.
In the interest of time, again, just any quick question? Maybe one? Jan. By the way, we'll just ask all in-person speakers to state your name into the microphone as you ask your question.
Thanks for that, Ryan. I have a quick question. The group quarters definition included group quarters. And so I was wondering if you could elaborate a little bit more on how that is defined.
Oh,
I mean, you know what I'm saying? It's group quarters is defined by other group quarters. So it was a little vague in the slides.
So group quarters, okay, I see what you mean. Okay, so group quarters are defined. There's 8. This is a coarse definition of group quarters, so there are multiple definitions just to make things more confusing. So this is the 8-level group quarters. So these are the major group quarters types. Something like college or university student housing, things like that. So that's one major group quarters type. GeoUnits without any group quarters are also included in that one. When I say combination of group quarters types, so GeoUnits that do not have group quarters is one combination as well. a good question.
Quickly, could you comment on the off-spine entity distance? Is this more or less telling us how many different noise values are going to get aggregated, added up in determining the accuracy for that entity?
In a way, yeah. It's how many you would have to add up in order to derive the entity. Yeah, exactly. So yeah, if it were OLS, then it would be kind of like the square root of that number you could multiply by that and also if the variance in each geo unit were the same, so that would be the square root of that multiplied by the standard deviation, which give you the standard deviation in this off-spine entity that you're thinking of. Yeah. It's a good question. Awesome. Thanks.